Alright, welcome back for our next installment in Chapter 3 on atoms and elements. This time we'll be dealing with isotopes and atomic mass. I've already been using the term isotope because I just couldn't help myself, but this is the part of Chapter 3 where we're really going to go into isotopes and see how atomic mass differs based on number of neutrons for the various isotopes of a given element. Alright, so let's go ahead and give a proper definition of an isotope. So isotopes are atoms of the same element that have different mass numbers. Because they're the same element, they obviously have the same number of protons. So in order to get those different mass numbers, they must have different numbers of neutrons. And they can be distinguished by atomic symbols. Again, not just the letters, the capital and possibly lowercase depending, but specifically a mass number and the symbol. The atomic number is often shown as well, but we don't really need that, right? We don't need to show 12 as the atomic number of magnesium because just showing magnesium means we have element number 12. But we do need the mass number if we're going to distinguish our isotopes. And just a reminder, isotopes were not originally in Dalton's atomic theory. He didn't understand that you could have elements that are the same element but certain atoms have different masses than others because of the number of neutrons. Alright, so if the chemical behavior is the same because each element has the same number of protons in its nucleus, the property here that differs is the mass. So the mass number is going to be different, and we'll show this by having an atomic symbol that includes a mass number. So mass numbers are in the upper left corner by convention, and then atomic numbers are in the lower left corner in the most common way we represent it. So here's an example where we see an atom of sodium with atomic number 11. That's sort of redundant, right? If it's sodium, obviously it has an atomic number of 11. But the key piece of information we've added to the element symbol is this mass number of 23. So if we're dealing with a mass number of 23, well, that means we must have 12 neutrons, right? 23 minus 11 equals 12. And that means that we have an isotope of sodium that has 12 neutrons. And potentially we could have other isotopes. Usually they have very similar neutron counts, so maybe 13 or 11 would be logical numbers. You wouldn't ordinarily see an isotope of an atom that has a lot more or a lot less neutrons than the stable isotopes. Okay, so if we're giving a comprehensive atomic symbol, we should be giving the number of protons through the atomic number, the number of neutrons through the mass number, and then electrons should equal the protons if it's a neutral atom. So that atomic number should also be the number of electrons. If that's not the case, then we'd have a superscript that follows the atom symbol that indicates the charge on that atom. If it's positively charged, that means it has additional protons compared with the number of electrons. If it's negatively charged, that means it has more electrons than protons. So here on the slide we see 3 neutral atoms, oxygen 16 isotope, so 8 protons, 8 neutrons to get us to 16, and then 8 electrons since it's a neutral atom. We also see phosphorus 31, so 15 protons is what makes us phosphorus. 31 minus 15 gives us a value of 16 neutrons, and then since we're neutral and had 15 protons, we must also have 15 electrons. Finally, that zinc atom, actually, if you remember our learning check from the last subtopic, we dealt with zinc 65. So here we see zinc 65 with 30 protons, that's what makes it zinc. 35 neutrons, 65 minus 30, the mass number minus the atomic number gives us the number of neutrons. So 35 neutrons, and then since it's a neutral atom of zinc, it must have 30 electrons to balance out the 30 protons. Okay, let's go ahead and pause here for a moment to do a learning check, make sure we're getting the information we need to be getting from this part of the chapter. Here, our learning check tells us that naturally occurring carbon consists of 3 isotopes, carbon-12, carbon-13, and carbon-14. And notice that's another way to represent isotopes, is just with the element symbol, a dash, and the mass number, because obviously the element symbol also gives us the atomic number if we were to be able to look at the periodic table, for instance. So for these, for carbon, let's state the number of protons, neutrons, and electron in each of the following isotopes. So if you can fill out the proton, neutron, and electron count for the carbon 12, which now we see in the more standard notation with the 12 superscript and 6 subscript, 13, and carbon 14. So pause the video if you haven't finished that yet and start it back up when you're ready to see how you did. Alright, so let's see how you did. Obviously for all the isotopes of carbon, we're going to have 6 protons, so you could fill that 6 across right away without even giving it too much thought, I hope. For neutrons, for the first case, 12 minus 6 equals 6 neutrons. For carbon 13, 13 minus 6 equals 7 neutrons. And then finally for carbon 14, we have 14 minus 6 equals 8 neutrons. And finally, since these are all neutral carbon atoms, they must have 6 electrons to balance out those 6 protons. So hopefully you were able to completely and correctly answer that learning check. If you struggled anywhere, we're going to be doing another learning check now, so you can hold out, see how that does. But if you're really having a lot of trouble here, please get in touch with me. Come and see me, or send me an email. Give me a chance to try to help you with understanding these concepts. So that chemistry builds on itself. If you really have a weak understanding early on, it's not going to get better as we go along. So let's take some time to address it. Alright, so in our learning check now, we're looking to write the nuclear symbols for atoms with the following subatomic particles. Number 1, we have an atom with 9 protons, 10 neutrons, and 9 electrons. For 2, we have 17 protons, 20 neutrons, and 17 electrons. And then for number 3, we have 47 protons, 60 neutrons, and 47 electrons. So go ahead and pause the video if you haven't finished your nuclear symbol, and then start back up to see how you did. Okay, so hopefully your symbols look like the symbols here on this screen. We have fluorine being the element with 9 protons in the nucleus. Because of the 10 neutrons, 9 plus 10, the proton plus neutron count, gives a mass number of 19, which we represent as a superscript to the left of the element symbol, and then the atomic number 9, the proton count, down as a subscript to the left of the symbol for fluorine. Number 2, now we're element 17, so we're chlorine. With the 20 neutrons, we have a total mass number of 37, and then of course that's 17 down below as a subscript before the element symbol. Finally, element number 47 is silver, element symbol Ag, and 47 protons plus 60 neutrons gives 107 for the mass number, and because we're dealing with a neutral atom, we have the 47 protons, and for each of these we have no charge shown because they're all neutral atoms. So hopefully that went well. If you're still struggling, guess what? We're going to do another learning check, so see how that goes, and then decide from there if you need some additional assistance. Alright, so in this learning check we have 2 questions. First of all, which of the following pairs are isotopes of the same element? And then a follow-up question to that, in which of the following pairs do both atoms have 8 neutrons? So go ahead and answer that, and pause the video if you need another moment. Otherwise we'll pick back up and see how you did. Alright, so for that first question, which of the following pairs are isotopes of the same element? Well, the best answer choice was B. We had atomic number 6 for both of those, and therefore we were dealing with isotopes of the same element. The first case, the leftmost case with a mass number of 12, has 6 protons and 6 neutrons. With a mass number of 14, we have 6 protons but 8 neutrons. And then number 2, in which of the following pairs do both atoms have 8 neutrons? Well, now we need choice C, right? 15 minus 7 gives us 8 neutrons, and 16 minus 8 gives 8 neutrons as well. So hopefully with these 3 learning checks, you've been able to assess how you're doing in this part of the chapter. If you're struggling, of course, get in touch with me, as well as working some additional problem sets, questions from the end of the chapter. But hopefully you're doing well, and hopefully things are making sense here in this chapter 3.5 Isotopes and Atomic Mass section. Okay, so at this slide we're going to look at some isotopes of magnesium. So magnesium has these 3 isotopes, naturally occurring isotopes, and they are magnesium-24, magnesium-25, and magnesium-26. And if we take a look, each of these naturally occurring isotopes of magnesium occurs in some natural abundance. So overwhelmingly, most atoms of magnesium are the magnesium-24 isotope. So as we see, that's 78.70% of the natural abundance, and therefore if we multiply that, the mass of the magnesium-24 isotope, which is atomic mass unit value of 23.99, when we multiply that by the 78.70%, and again divide it by 100 to make it a percent, we get a value, a contribution to the overall average atomic mass of 18.88 atomic mass units. When we do the same thing with the magnesium-25 isotope, now its mass number is, or its atomic mass is 24.99, multiplied by its percent abundance, 10.13%, divided by 100 to make it a decimal. That contributes 2.531 atomic mass units toward the average atomic mass of magnesium. And finally, the heaviest isotope of magnesium, magnesium-26, has a mass of 25.98 atomic mass units. When we multiply that by its natural abundance, 11.17 divided by 100 to make it a decimal, we get an additional 2.902 atomic mass unit contribution. So if we look at the average atomic mass of a random magnesium atom, it should have an average mass of 24.31 atomic mass units. Of course, none of them have exactly that mass, right? That's a mass in between the magnesium-24 and magnesium-25 isotope, but that's our weighted average. Again, it's based on the natural abundance of those 3 magnesium isotopes. So that's the value, that 24.31. That's what we see on the periodic table that you would use for your exams. That's the average atomic mass. And we do that because we have a lot of atoms in most of our reactions. So we're mainly looking at what that average does to the mass of magnesium when we're going to have some magnesium-24, some magnesium-25, and some magnesium-26 present. If we consider sulfur, on the other hand, sulfur has 4 naturally occurring isotopes, and we see those percent abundance. Sulfur's overwhelmingly sulfur-32. That's the isotope that's in greater than 95% abundance. But we do have small amounts of sulfur-33, a little more even of sulfur-34, and then finally a very small amount of sulfur-36 that occurs in nature. So we do have to consider each of those. Obviously, the mass number for sulfur-32 is going to be very close to the average atomic mass because of its huge percent abundance, but we have to also consider the contribution of those other isotopes, because if you have a sample of sulfur, you're going to have some of each type of sulfur isotope represented, even though it's overwhelmingly sulfur-32 in the sample. Alright, so now we see an atomic mass here listed under the element symbol. So this is like our periodic table that we use for the exams. We also happen to have the atomic number above the element symbol, but this atomic mass is listed below the symbol of each element on our periodic table. It gives the mass of an average atom. So even though that mass might not represent any particular isotope, it represents the average sample that you would be interacting with. It's not the same as the mass number, right? The mass number we said is a whole number based on the number of protons and neutrons in a given isotope. This is calculated using a weighted average, which depends on the natural abundance of each of the naturally occurring isotopes. If you look carefully at our table, and if you're drawn to those heavy elements like I always am, you probably notice that some of these elements underneath them, they have their atomic mass with parentheses, and that just indicates that there are no naturally occurring isotopes for that element, and instead we've given the mass of the most stable radioactive isotope. So that tends to happen especially as we get into those really heavy man-made or human-made elements that we've discovered in only the recent decades, as compared with all the early elements, the elements up to 92. most of those have at least some stable naturally occurring isotopes. Alright, here we see table 3.8, and that just lists a few elements and their stable isotopes. And again, most elements have 2 or more stable isotopes that will contribute to the atomic mass of that element. That's not always the case. If you look at fluorine, fluorine has just 1 stable isotope. So all the fluorine atoms that occur in nature that are stable, non-radioactive, they're all fluorine-19. For lithium, which is a much lighter element, we happen to have lithium-6 and lithium-7. Carbon, we've already talked about the idea that carbon has carbon-12, carbon-13, and carbon-14 that occur in nature. Carbon-14 is natural, but it is also radioactive, so we have used that for carbon dating, and we'll talk about that in the radioactivity section in this course as well. Oxygen also has 3 isotopes, 16, 17, and 18. Sulfur, we just reviewed that it has those 4 isotopes. And copper has 2 stable isotopes, naturally occurring isotopes, 63 and 65. So as we see, looking at the average, weighted average, the atomic mass that would be listed on the periodic table, we could correctly assume that lithium-7 is going to be the predominant because our mass is almost 7. So lithium-6 must be present in much smaller amounts. Carbon-12 is the predominant carbon isotope. Oxygen-16 is the predominant oxygen isotope. Fluorine-19 is the only naturally occurring fluorine isotope. And then sulfur, again, that mass is just over 32 because 95% of sulfur occurs as sulfur-32 isotopes. And finally, copper, 63, 65, those are pretty close. If we were right in the middle, we'd be at 64. So the fact that we're closer to 63 suggests that the copper 63 isotope is the most prevalent, but it's not a whole lot more prevalent than copper 65. If we were just over 63, that would tell us we have overwhelmingly copper 63, but the fact that we're 63.55 suggests that there's a significant amount of copper 65 out there as well. Okay, if we look at the atomic mass for chlorine, that's based on all the naturally occurring chlorine isotopes. And again, I have to be very careful because we do have naturally occurring radioactive isotopes, and they do count toward that mass. So it's just that they're naturally occurring, and the only time things get interesting and when we get those parentheses that I mentioned before is when we have no naturally occurring isotopes. So atomic mass is not usually a whole number because it's a weighted average, and it's all based on carbon-12, and the fact that carbon-12 is only one of the carbon isotopes means that even carbon doesn't have exactly 12.00 on the periodic table. It's 12.01. On our periodic table that we use for the exams. And for chlorine, for example, it's the weighted average of the chlorine-35 and chlorine-37 isotopes. So the fact that we're 35.45 suggests that chlorine-35 is the more predominant, but there is a significant amount of chlorine-37. Just like our copper example, where the copper-63 was more prevalent than the copper-65, for instance. If we're given the actual percent abundance for the chlorine-35 and chlorine-37 isotopes, then along with their masses, we can find the average atomic mass of chlorine by taking the mass of the chlorine-35 isotope, which is 34.97 atomic mass units, multiplying it by 0.7576, which is the 75.76% abundance divided by 100, and we get the contribution from that isotope as 26.49 atomic mass units toward the average atomic mass. When we consider that the chlorine-37, which has an atomic mass unit mass of 36.97, multiplied by the 24.24% abundance, again divided by 100 to make it a decimal, that contributes another 8.962 atomic mass units toward the average atomic mass, and we find that the weighted atomic mass of chlorine is 35.45. So it's a fairly straightforward process as long as you remember the steps and you're given the mass and percent abundance for all the naturally occurring isotopes of a particular element. So just like for chlorine, if we're looking at the atomic mass for magnesium, the atomic mass of magnesium is based on all the naturally occurring magnesium isotopes. It's not a whole number, and it's the weighted average of the magnesium 24, magnesium 25, and magnesium 26 isotopes. And if you recall, back several slides ago, we saw that magnesium 24 is the most abundant magnesium isotope, and that's why our average atomic mass for magnesium 24.31 is closest to 24 based on that abundance of that magnesium 24 isotope. Okay, and so to review again, if you remember this slide from a while back, so we're looking at the magnesium 24, magnesium 25, magnesium 26. If we take those mass numbers, each multiplied by its own percent abundance, expressed as a decimal, get the mass contribution from each of those isotopes, add them all together, we end up with that average atomic mass. Okay, so we just did it for chlorine. Now we're doing it again here for magnesium. Okay, so let's see how we did. We took the time to review magnesium. Let's see if you can give the average atomic mass for some of these other metal elements. So calcium, aluminum, lead, barium, and iron. So this is using your periodic table, the one that you have there under content or Blackboard, so that it says periodic table for exam use. Hopefully you remember it from using it for exam 1, and jot down those atomic masses for each of those elements. Okay, so hopefully you were able to glance at the periodic table and just take the mass number below the element symbol. So calcium, element symbol capital C, lowercase a, has an average atomic mass of 40.08 AMU. Aluminum, capital A, lowercase l, 26.98 AMU. Lead, capital P, lowercase b, 207.2 atomic mass units. Barium, capital B, lowercase a, 137.3 atomic mass units. And then finally iron, capital F, lowercase e, 55.85 atomic mass units for its average atomic mass. So hopefully this was relatively simple. Probably the only mistake you may have made is having the wrong element symbol or not having your periodic table handy and not pausing the video in time. But hopefully you were able to transpose all those numbers from the periodic table and got them correctly addressed. If not, we've got another learning check coming up, and we'll see how it goes that time. Alright, so as promised, here's another learning check, a final learning check for this subtopic on isotopes and atomic mass. And this learning check tells us that the atomic mass of chlorine is 35.45 atomic mass units. Based on this information, which of the following isotopes of chlorine is present in the largest amount? Is it A, chlorine 35, or B, chlorine 37? So hopefully you've already made your choice. Otherwise, pause the video now and we'll see how you did. Okay, so based on the fact that the atomic mass of chlorine is 35.45, and our options were chlorine 35 and chlorine 37. Of course, if we were 50-50, we'd expect a value of around 36 for the average atomic mass. Instead, we're at 35.45, which means we're more abundant in the chlorine 35 isotope. That's why our value is closer to chlorine 35, and hopefully you selected chlorine 35 choice A as your answer choice for this final learning check for isotopes and atomic mass. If you're struggling with this material, there are a number of end of chapter questions you can try. There's even 1 or 2 homework set questions that get at this idea. So if you've tried those, it's still not making sense, please reach out to me. Let's figure out where you're having the difficulty and let's get it addressed so that you can move forward in the course and build on this isotope and atomic mass concept.